Today I'm going to talk about interactive introspective C++ at CERN. And before I start, I have to admit, guys, you set the bar very, very high. And I plan to run away, but I have a flight to catch on Saturday, so I'm sort of stuck. Uh, what I'm going to try to explain to you today is the way that we use C++ at CERN in the context of our big data analysis. And I want to do a top-down presentation, and I want to, because usually what you get from CERN, you get the nice movies which are for the general public. And then you see huge impressive things, and then the string, how this binds to the computing, it's sort of not very well described, and this is because it's for the general public. And now I think I want to go through the whole chain and explain to you what we do. So I'm Vasil Vasiliev, and today I'll try to do that. And before that happens, I would like to thank the organizers for having me here. And I apologize for my English, but if you think it of the how full size, when again you are going to hear Bulgarian English, right? So, how many of you guys have heard about CERN? That's pretty good. And how many of you have watched the movie? Or read the book? So, as a matter of fact, I ended up at CERN because I read the book. I find it really impressive, and in the end, it got a lot of things in the wrong way, but it worked for me. I thought I am a computer scientist in the end, and I never thought about things like that. I never thought that somebody is trying to create antimatter, for example, and this made me go and search for it, and I found out that's actually true. And then I searched for the organization CERN, and then I really found out that there is such organization which is able to do that. But the first myth was busted, because in the movie and in the book this was a top secret organization, more or less like Area 51 or something, and it wasn't. Everything was on the internet, everything was explained very well, and damn, it wasn't a top secret organization, but it was interesting. So it was quite friendly for newcomers. I saw that there were many positions for students. They liked students, and I applied. And after a couple of unsuccessful applications, maybe because of me, because I didn't do the paperwork correctly, but that's my excuse, I get accepted, and then I got a position later on. So, and then I understood that it's very, very different from what the movie was showing to us and what the book was showing to us. But in the end, it did the job. And when I went there, I saw that all those white coats were total myth. Nobody does that at CERN. So, and of course, if you see the movie, you're going to see something like that. That's the antimatter trap, which was hidden somewhere in the Vatican, and they had to find it. And as a matter of fact, I found it first, but this doesn't end up in the movie somehow. I don't know why. So, but please take a look at the antimatter trap, and then I'm going to show you what it looks like in reality. So more seriously, so what is CERN? I guess most of you already know, but it's a laboratory that is targeting in particle physics fundamental research, which was proven to be very interesting to the people all the time, right? People were interested in understanding what the world is made up from, what it consists of. And in the ancient times, for example, the old Greeks tried to come up with a model, right? They tried to understand and try to specify the building blocks of the world. And of course, they came up with something nowadays which is completely insane, but they came up with the world consisted of earth, fire, air, water, and something they call ether, which I have no idea what it is. But later on, that quest continued, and we discovered the chemical elements, and then with the atoms, and you know the story. And now we know that the atoms are not the building block, the atomic structures of the universe. So we discovered that they are made of something, and that something is very, very hard to understand what it is, because they are so strongly connected that you can't really understand what is in there. So what we do is we have a huge accelerators which help us to accelerate those particles and smash them one into another. And then we have a huge, sort of say, microscopes called detectors, where they are meant to investigate all those debris which are coming from the collisions, and this gives us a clue how things are made. And of course, it's a huge organization. It's the world's biggest high energy physics laboratory, and it has 3,500 members of personnel, many users. And if I can explain it, it's on the boundary between academia, science, and industry, because you have huge projects that you have to do it together with the industry, and then you have the research which is on top of it, which I find it really, really nice. So maybe most of you know, but there are lots of experiments at CERN which are targeting very, very different things. And for example, we have general purpose experiments such as CMS and ATLAS, which have the goal to understand general physics. So they look for the Higgs boson, they look for dark matter, they look for all the variety and the wide range of things that can happen. And there are two, because they have to cross-confirm their discoveries in the end, right? Because if you have a bug in the software or miscalibrated detector, of course you're going to see a lot of particles, and then you're going to publish them, and then they're going to be brought at school, and things go wrong. So those are mainly the two general purpose experiments. And we have more specialized experiments like LHCb and ALICE, which are targeting in very specific properties of the matter or the particles. For example, LHCb is trying to understand what is the measurement, what are the properties of a certain quark called beauty quark or B quark. And then they have an assumption that the antimatter representation of that quark is going to be different from its original one. So ALICE, for example, is targeting at investigating what we call quark-gluon plasma, when you don't hit two protons together, but two ions with a lot of protons in between, and this brings high energy densities. And those high energy densities may interact differently. So we have all those specialized experiments and general purpose experiments, but four biggest ones are ATLAS, CMS, LHCb, and ALICE, and those are on the ring 100 meters below ground. But we have different experiments. We have underground experiments, and we have on-ground experiments, and we have experiments in the space. So the other kind of experiment is, for example, CAST experiment, which is targeted in investigating for the theoretical particle called axion, which should be produced in the core of the sun because of certain conditions. And we have another one, which is another experiment called AMS, which is on the International Space Station. So I want to give you a little bit feeling about that, and I'll try to keep it short so that I can really become technical very soon. So as I said, I just want to give you the magnitude of the experiments, what they look like. So ATLAS is one of the general purpose experiments, as I said, and it's targeting a lot of things. And you can see that experiment nowadays means not something that you can set up and tear down in a day. Those are huge machineries that are run by huge collaborations of people, and in the case of Atlas, there are more than 3,000 engineers and scientists and other people that are helping to run that. And to my surprise, for example, you can't see it very well, but it weighs 7,000 tons, and the cables that are around are like 3,000 kilometers. So, and those experiments have their own code base, which helps them to reconstruct the events that they observe. Because in the end, the electronics give you, or the subsystem of the experiment gives you something that like that system was hit by something at that point. And then you have to bring it up, and you have to understand what it is, whether it was a particle and things like that. So that part of the software is around 5 million lines of code for an experiment. And again, that CMS, its purpose is again like Atlas's, but it's run of considerably more people are involved in it, and its purpose is the same, but its design and architecture is completely different. So this again helps to cross-check what has been discovered by the rest of the experiments. So this is very important. So we have different, and those two experiments are exactly at the beam line. So the beam line crosses exactly at the center of the experiment. And those are different ones, which, for example, LHCb, which is a specialized one, is an experiment which is not on the LHC, but it's a little bit not on the beam line, but it's a little bit away from it, investigating for certain kinds of particles, certain kinds of event. Not any kind of event, but certain kinds of certain properties. And it's run by a lot less people. But to my surprise, their code base it's huge. They have like 6 million lines of C++. And the same holds for the ALICE experiment. It's again in the cavern, and I don't want to give you that many details. So, and that's not Star Wars. That's our International Space Station. And interesting thing for the IMS is that it's a relatively new experiment, and it was brought into space by the last flight of the Endeavour space shuttle. So besides accelerators, I think it's worthwhile mentioning that we have decelerators, and those are the anti-proton decelerators that we have. So this facility basically tries to create antimatter, and the antimatter is once the particles, the antiparticles are created, they have to be decelerated, because the creation of the particles happens when you're shooting beam onto fixed target, and that thing scatters, and some of them become antiparticles, produce antiparticles, and those antiparticles have to be catched by the accelerator, which has to sort of say slow them down, and then they are put in the so-called traps, and those are huge magnets like that. This has nothing to do with the movie, and this is one of the traps, the antiparticle traps, which the antiparticles are held, and then in those traps, when they got those antiparticles, they try to build up anti-atoms, and nowadays they are able to build anti-atoms of hydrogen. They are able to build anti-hydrogen, and then the theory says, of course, anti-hydrogen has to be exactly like the hydrogen, but in practice they are not sure, and they try to investigate whether that's true or not. And so far there are slight differences between the hydrogen and that anti-hydrogen. But of course, in the movie, they say that like that you can produce 1 gram of antimatter, and that's not true, because it is very, very, very inefficient. And the energy amount that you need to consume to produce 1 gram of antimatter, they calculated it because, of course, they had to come up with real facts. Is 10 to the 15th of euros. So you can imagine the number of money that you need to pay for the electricity, if you have it, to create those amounts of matter. And if you have the money, the amounts that we are able to produce are like we're going to get 1 gram of antimatter after 1 billion of years. So you can imagine that this is nothing which can be with a movie, but still, I wanted to make that bridge. And of course, here my explanation is a little bit from the point of view of a computer scientist, and I know people that are very, very not very confident, even they have worked a lot of time at CERN, they're not very confident that they can describe properly what the organization does, because the organization does a lot of things. It's not like that they are hidden, but there are a lot of things, and nobody knows in the end everything, right? So, and I was discussing that issue because I think it's an issue. I worked there for 3 years, and now I have to try to explain what it does. And I spoke about that with my friend, and he said, well, show them pictures. And here I'm showing you pictures. He said, a picture worth thousands of words. And I said, okay. So if that's true, then if I can show them 24 pictures per second, this means like 24 times 1,000, which means a lot. And this is an example how a bad interpretation over extrapolation works. So, but anyway, I want to show you a movie instead of trying to show you how the entire accelerator complex works. I prefer to show you a quick movie, like 6 minutes, so that you get the impression what happens. And from there on, I'll try to guide you through the whole data taking and data analysis and simulation process, and what do we do in the end. So, how that thing works. I have to do. Yes, please. No, I think it's okay. Yes, and I guess. So shall I start it? Let's see.
Insignificant though this bottle of compressed hydrogen gas looks, it marks the beginning of the world's largest and most powerful particle accelerator chain, culminating in CERN's spectacular Large Hadron Collider. Hydrogen atoms from this gas cylinder are fed at a precisely controlled rate into the source chamber of a linear accelerator, CERN's LINAC-2, where their electrons are stripped off to leave hydrogen nuclei. These are protons and have a positive charge, enabling them to be accelerated by an electric field. Their journey to eventually take part in ultra-high energy collisions similar to those following the Big Bang can now begin. This initial acceleration has caused LINAC-2 to be likened to the lumbering first stage of a huge rocket. By the time this packet of protons leaves LINAC-2, it'll be travelling at 1/3 the speed of light. It's about to enter the booster, stage 2 of the rocket, if you will. In order to maximise the intensity of the beam, the packet is divided up into 4, one for each of the booster's rings. Straight acceleration is now impractical, and the booster is circular, 157 metres in circumference. In order to accelerate the packets, they are repeatedly circulated, and the electric field is now pulsed in the same way that you push a child on a swing each time they reach a certain point. Magnets exert a force on the passing protons at right angles to their direction of motion, and so powerful electromagnets are used to bend the beam of protons round the circle. The booster accelerates the protons up to 91.6% of the speed of light and squeezes them closer together. Recombining the packet from the 4 rings, it's then flung on into the proton synchrotron, by analogy stage 3 of our rocket. Let's just follow 2 such proton packets. The proton synchrotron is 628 meters in circumference, and they circulate for 1.2 seconds, reaching over 99.9% of the velocity of light. It's here that the point of transition is reached, a point where the energy added to the protons by the pulsating electric field cannot translate into increased velocity, as they're already approaching the limiting speed of light. Instead, the added energy manifests itself as increasing mass of the protons. In short, the protons can't go faster, so they get heavier. The microscopic kinetic energy of each proton is measured in units called electron volts, and now the energy of each proton has risen to 25 giga-electron volts, or GeV. The protons are now 25 times heavier than they are at rest. The packets of protons are now channeled into stage 4, the superproton synchrotron, a huge ring 7 kilometers in circumference, designed specifically to accept protons at this energy and increase it to 450 GeV. Soon, the packets of protons will be energized sufficiently to be launched into the orbit of the gigantic Large Hadron Collider, or LHC, which lies between the Jura Mountains and the Alps, and straddles both France and Switzerland. Lying deep underground, it has a circumference of 27 kilometers. There are 2 vacuum pipes within the LHC containing proton beams traveling in opposite directions. Using ultra-sophisticated kickers to synchronize incoming packets with those already circulating, one vacuum pipe has injected into it protons which will circulate clockwise, and the other protons which will circulate anti-clockwise. The counter-rotating beams cross over in the 4 detector caverns, where they can be made to collide. The energy of the collision is double that of the individual opposing protons, and it's the debris from these collisions that is tracked in the detectors. For half an hour, the SPS injects protons. Finally, there are 2,808 packets. During this time, the LHC adds extra energy to each proton, whose velocity is now so near the speed of light that it goes round the 27-kilometer ring over 11,000 times each second, getting a boost of energy at each revolution from the pulsed electric field. Finally, each proton has an energy of 7 tera-electron volts, and they're 7,000 times heavier than at rest. The magnetic force needed to keep the beams bending to the ring is so enormous that nearly 12,000 amps must flow through its electromagnets. This is achieved by making the LHC colder than outer space, so that its magnets become superconducting. Now the protons are ready to collide in the detectors. A steering magnet finally brings them onto a collision course. The total energy of 2 protons colliding in the LHC is 14 tera-electron volts and reproduces similar states to moments after the Big Bang. Particle tracks from these collisions will be analysed by computers connected to the detectors, and it's hoped these tracks will give a new insight into the very birth of our universe, how our universe has evolved, what governs its behaviour today, and where it's going in the future.
So, that's pretty much it, and from here on becomes a little bit less spectacular. So, of course, we. By the way, can I use that thing works because my battery doesn't. Sorry. Yeah, but it doesn't. No. I'm sorry. It's kind of weird system.
So it's still not working?
No, it doesn't. Yes, it worked, but for a while. Yes, that would be fantastic.
Try with this. Maybe the adapter is not
Yeah, yeah.
a little held through.
Yes, good.
Works.
Thanks. Saved my life. So, and in the beginning, when LHC was designed, they had to do the calculations about the computing power that that would be needed for the experiments, and very quickly they understood that the funding that they have is not enough for storing all the data that is going to come, all the predicted data that is going to come from the 4 experiments. And of course, even though the CERN Computing Center was and still is very, very big, it wasn't enough. But they had collaborating organizations like universities and whatnot, which had access to regional data centers and data storages. So this was the main invention at that time, so-called computing grid. So the idea was to connect them together, and so that they can work in that context. And of course, in the same context, they had to share the data. They had to share information between all the organizations and all the collaborators. And this is how WWW was born. From doing a fundamental research. So we have different tiers, and tier 0 is CERN Computing Center, which serves as a hub for data, where all the experiment data would come, and then it would be distributed from one of the tier 1 computer centers, which are all around the world. We have 11 of them, and you can see that we have computer centers in Lyon, France, in Taipei, Chicago, BNL, I think on Long Island, and so on. So tier 2 is the computing resources, which are in the universities, which are relatively small, and they replicate the data, and they can further analyze it. And then tier 3 is the user resources that are used to analyze the data. So I'll try to be a bit more quicker because I'm very, very far from where I want to be. So what is usually the data flow? When the experiment sees an event, it sees a lot of events, a lot of things happening in the experiments. And usually, if you would store everything that an experiment would see, that would mean that you have to store 1 petabyte of data per second. And interestingly enough, very tiny amount of that seen data is interesting for physics and for the physicists, for the high energy physicists. So an online trigger and pre-selection and data acquisition system filters out the uninteresting events, and then the rest of them goes to the so-called reconstruction, where from just a signal which something hit somewhere, you have to transform it into an electron. This was likely an electron which had that angular momentum and that energy. So that is the partial reconstruction, and then you have the event summary data where the actual thing is described. Of course, you have a simulation part, which gives you an very important information about the calibration of the detector, and then you have to verify it against the data that you have, so that you make sure that the data taking is very precise. And of course, then the interesting part here is the offline analysis, which I say offline analysis means that this is an iterative process of the data which were stored by the experiments, and that data then is analyzed by the physicists in a way that they are looking for interesting events, and they are trying to see a trend, or they're trying to see something and try to explain it. And that thing happens by using an analysis algorithms, and those analysis algorithms are very, very specific to the physicists, because this is basically the frontier. And providing services for the physicists, you can't really predict how that data is going to be accessed, or what a physics analysis would be in like 10 years. So you have to be really, really flexible in that respect, so that you provide the physicists with the tools that they might possibly need. But in the end, everything follows a pattern, which I will explain. So physics analysis usually, most of the time, you can think of it as a C++ program. And that C++ program works on a subset of data that the concrete physicist is interested in. So usually it interfaces with a lot of libraries. As you saw, there are many steps. And suppose that all the steps were implemented in a different way by a different team, in different programming language. This would be a huge interoperability issue. And this is something I'm going to talk briefly about. And of course, in the end, CERN is very friendly to the newcomers, which means that they have a lot of students, a lot of novices in the computing, and even good physicists. They're not very experienced programmers, because for them programming is a tool, just the way that the car is a tool for me. I don't need to understand how the combustion works or something like that. So if you implement the steps of analysis in separate libraries and with separate concepts, that would blow up. And there were two very, very smart people, René Brun and Fons Rademakers, which were able to foresee that, and they started a framework for big data analysis called ROOT. So how many of you have heard about the framework of ROOT? Yes, I agree that the name is very ambiguous, but so it is, in short, a framework for data processing born at CERN, at the heart of the high energy physics, and every day thousands of physicists are using it to analyze and perform their simulations and to analyze their data. So it was started in 1995, and they had that vision about, if you try to implement everything in a different way, it doesn't work, at least in the CERN context. It's not the industry. I mean, it's not like you can have a bunch of libraries and then the user pick it up, because I mean it's very difficult for the users to find their way through. And they had the single language concept. They are using C++ for almost everything. So they use C++ as a common denominator. So in the end, every experiment have their software stack, but the commonalities of the software stacks are the root framework. So that's the bedrock of the offline data analysis. And soon it became the default / only tool for analysis in the high energy physics. And then they realized a lot of other domains. They realized that this is something which is we have similar problems in the end, and we have use cases where that framework is used in astronomy and finance. Of course, you don't know how finance are using it, but we know that they're making good money because they're financing our workshops and stuff. So, and in the end, as everything which is developed by CERN and funded by the general public, it's an open source, so you can download it and start playing with it. So what is all about? If I have to place it at some point, I would say it's exactly between the boundary between physics and computing, because you saw that picture and you saw the data intake. So basically everything comes from the experiment as C++ object and C++ objects. And those C++ objects, you have to be able to save them, access them, process them, show the results in the end of what you've got. And interactively, in a sense, that thing has to be easily extendable by the users, because you cannot really foresee how it's going to be used, but you have to provide the tools of simplifying the things. And as I said, if you cannot predict it, we know the pattern that an analysis is built. So almost everything starts from, let's try to do that. What happens if I do that? Something very simple. And then later on, they start, okay, that was good, but then I want to continue. I know what I want to do conceptually, but I'm not sure how to do it programmatically. So, and exploratory programming and the read evaluate print loop concept that we have is very important in that case, because it allows the user to quickly and easily prototype what he thinks he needs, and then he can easily verify whether that is the one that he needs, or he has to slightly change something, and then get the result. So, and we have an interactive shell-like prompt where you can type C++. Don't bash me yet. So that is proven to be very helpful, because in the end you need to know what that library does, and does it do it in a way that you expect it to do. And in the common case, nobody writes documentation, right? Well, if you ask a developer to write documentation, then he says, well, are you arguing against my code? It's really something that is self-explained. You can understand it. It's very, very concise, and you can understand it. And if you ask a user to read the documentation, he would usually say, am I that dumb? I can find my way through without any help. So it's a little bit of ego on the both sides. And I claim that documentation is good enough. It's good. But you have to be able to verify what you have underlying that documentation, whether that fits, even though you have that very nice documentation. And the way that we're providing to the users to be able to poke up a little bit the libraries and then understand what they need. So after a certain iteration, they find their way through, and they afterwards can compile their analysis and send it off to the computing grid. But this is how the exploratory programming works in our context. So they have to, because they have a bunch of stuff that they usually don't know how to use. And that's okay, because we have like 1,200 classes, which are split into 60 different libraries in more than 19 categories. So starting from containers, which implements the basic containers, and ending up to SQL and networking. So in the end, nobody can learn. Well, there are very few people that can learn 3.5 million lines of code. And this is only the delta that they have on their software stack. So it is that is a key motivation here, and I want to make sure that I get it correctly. So the way that the user interacts with the framework, with the root framework, is that he can use it as a tool. He can open up some file which has data stored in, do some analysis and stuff iteratively, and then he can provide that analysis to the computing grid and so on and so forth. But most interestingly, this is the interface that they interface with their software stack. So this is the door that they can use, the same approach that they have learned using root, and the same approach like interfacing with 60 libraries, they can interface with 160. So by analogy, it's pretty much like Lang. You can use it as a tool, as a compiler, but you can build tools on top of it. And so, getting to the meat, the key property of our data is read once, write once, read many. So you have that data that came from the experiment, and you want to keep it around for, I don't know, 20 years, a long time ago, after the experiment is shut down. We have such kind of data from shut down experiments which needs to be processed. And that thing piles up. We provide a special file format, which I'm going to talk about, which nowadays store 180 petabytes of C++ objects. And this is basically all experiments data. It's very well optimized for sequential and aggregated reading, so this results in disk friendliness and low latencies due to the less round trips. And the file format by itself, it's a binary file format which is machine language architecture independent, which means that, and it is self-describing, which means that you have the contents, they are well described in the file format, and the way that you read the contents of the file are described as well, So that is proven on the next slide, because we have a JavaScript implementation which is able to read the root files completely independently on the platform, on whether or not you have the framework installed and things like that. So I find it really, really, really good. And the way that we store the data is interesting. And I can say that I'm not an IO expert. I work on the other part, which I'm going to show you in a few minutes. So what we do is what now industry calls vertical data storage. And we add to it recursively. We call it column-wise data storage, but that term is much more cooler. So what we do is you have the object, and you have the data members of in the object, and those data members you want to store, right? And those data members, if they're recursive, so you have to store recursively all the data members that are aggregated in that object, and that results in surprisingly high performance reading and better compression rate, and I'm going to show you how. But this was a very abstract explanation, so let's go through an example. We have a class, my class, and we have 3 objects of it. That's okay. So you can see here that the relevant part is the data stored in that object. We have accessors, we have methods, we have much more volatile things that can change. So what we do, we store the data members in a root file, which results in less data to store, and then we store the rest of it in a library. And here you can say, yeah, of course, but they'll go out of sync, and that's fine. If they go out of sync, we have a subsystem which we call schema evolution. So suppose that you had in the file std list, and then in your library, some version after that data was stored, some version of it, you change it to an std vector. We have an automatic schema evolution which map the straightforward cases automatically, so you can that data can be read into the new format. And for the non-straightforward cases, you can implement the readout on your own. But this is very important because we can rebuild the class layout without the library to be loaded, right? because you can create a sort of POD or something, and then you can selectively read things. And what we call vertical data. So this is, so usually when you read, you have a different optimization structures. This helps you the fast readout. But it appears that if you store your data in an optimization structure, this helps a lot because you can do selective reading, of course, depending on the context and depending on the data structure. But we use trees for that, and you can imagine, you can see it here that we have 3 objects, but those 3 objects are not stored sequentially because you have all those jumps and you don't know, you have to read them and discard them and things like that. So instead of that, we do we store in the tree, every member gets a branch, and then you can do the selective reading, which is very powerful because, for example, for some reason, your filter, you can filter for the in the first field, and then you need to understand whether you need to read more of that object depending on that first field, right? If it says that's not an interesting event or that's crap, you don't want to know about it, and on and on. And if that's interesting, you get that offset, and then you know all the offsets from here on. So and more importantly, of course, we deal with reading and writing, right? And in C++, that's not very straightforward because you don't actually, when you're reading it back, you don't know how much, what was the size of that thing that you want to read and how much to read. So you need some sort of reflection information. And right now, maybe soon this is going to be changed, but right now C++ has limited support of reflection information. So we have to do something about it. We have to have the reflection information which shows us how much we need to read in order to make it work, right? And this is basically our entry point for our reflection layer in root, and this is deriving from an entity called T-class, which is able to reconstruct. And when you're reconstructing a class, again, you can selectively reconstruct the reflection information from that class, and you can get information, for example, about the list of base classes, about the list of data members and things like that, offsets and things like that. And as I said, it's limited in C++, but we have to do something about it. And the only way we can, if you want to know about sizes and types and stuff like that, who else you would ask but the translator, either the compiler or in our case, the interpreter. Don't bash me yet. I didn't explain what I mean by interpreter. So in the case, our reflection layer, we have a built-in interpreter which served its purpose a long time, and this is our way of understanding what type means and all the details that we have. So what we do is we open up the interpreter internals so that it is able to send information back to our reflection layer about the types. And this is something that we do string-based because various reasons. Because it is, to begin with, platform independent, and it is proven to be very convenient. So everything in root heavily relies on that. So the interpreter is the glue between the systems because we have a plugin manager which communicates with that via strings and stuff. We have language bindings which work on that. Our I/O system, that's vital for it. And that's why I want to justify the role of having something interactive where in the process of reading and rebuilding things, you can poke it and it can give you an information back, besides of the other key strengths. Because it is important to be a bit more dynamic. If you have a prompt where you can write C++, you have to be a bit more dynamic. You cannot expect people to, I don't know, write compilation flags, link in libraries, and stuff like that. Everything has to be a bit more easier. And in that case, I didn't mention our auto-loading system, but I don't. If I have time, I'll try to explain what it is about. But it figures out automatically the missing symbols. It knows which libraries to load and which header files to pull in, so that you do my class and it would understand where that thing comes from, and then it will do basically the compilation, the linking for you. And in the end, the interactivity that's over the years that was proven to be very helpful, both in learning the framework internals and learning C++, which is important in our case, very, very important. And let's go back one step. Let's go one step back. So we provide language bindings. So what we have is that is how our prompt looks like, and then you can execute things. And I'm going to go in details about that. But here, the important thing is that you have a sort of Python engine which you can type Python, and you can bridge both worlds, and the same thing as Ruby. So I'm going to. What is more interesting is that we have you can switch back and forth between C++ and Python. So if you want to do certain things in Python, you can switch to the prompt, and when you're bored, you can Control D and go back. And the most interesting part is that because of our reflection layer, we're managed to bridge both worlds. Of course, as long as the semantic means something. So here, for example, I can define a std vector of int, push some element in that, then I can switch to Python, and then I can iterate over that. And you can see that this is translating the both concepts. It translates the container, the C++ container, in its semantic equivalent in Python, so that you can do this kind of thing. And that is because it relies on our reflection layer. And if one thinks of the model view controller paradigm, you can think of that as just a view or a controller, and the model is our reflection system. So, Sint, talking about interpreters, that thing, that is our production interpreter for over 17 years, and it was written in 1991. And for me, of course, it has its disadvantages, but it laid the foundation of our understanding of dynamic C++. It is, of course, it was made to support C, and then C++ was patched. It doesn't have good diagnostics, but whatever. So that is our motivation to go a bit more bold. So what we always wanted is we wanted full C++ support, and by full C++ support, I mean supporting the standard, doing the things in the same way that your compiler would do it, and it was very, very hard to do it with Sint. We had a hard time doing that, and maybe that looks funny for you, but for me it's a huge challenge, because it's a huge advantage, because we didn't do that. We had to hide certain parts of STL, for example, because our interpreter would choke up with it, and we have to be able to go to the new standards, and that is very, very difficult to hack in the interpreter. And we want better type information and representations. So we wanted proper redeclaration chains. We wanted proper template instantiation chains. We wanted proper macro expansion chains. We wanted proper, I don't know, type defs which are not going anywhere. And we wanted always to compile in memory and to be binary compatible, which was very hard in the previous days, because the previous interpreter had very limited knowledge about the target. So what you would do is, if you want to call natively, you would compile trampolines in a dictionaries where they will set up the stack so that you can make the call into native libraries, and that becomes particularly ugly when you have templates, because in order to do that, you have to have all the template instantiations with all the possible template arguments that you can instantiate, and that thing is, and in the end we wanted to be lazy, so we wanted to maintain less code, and maintaining 400k lines of code is very difficult. And in our case, our prototype is, and we are adopting it, it's more or less like 15k. So I always, we continue to try to improve things, but I always wanted, I always thought that we want too much, you know, because I mean, it was, for me it was just too much. And then we came across LLVM, and it was fantastic because we had that fantastic compiler infrastructure and that fantastic community, and we had everything there. So, but there was one issue. So it was a compiler library. So we had to figure out how to match it to make it work in the way that I have described, to be a little bit more dynamic, a little bit more user friendly, put it that way. So what is Cling? I would say it looks like an interpreter, and it behaves like an interpreter, and feels like an interpreter, but is it an interpreter? I don't know. I would say it depends on the community you ask. If you ask the duck type community, they would say definitely yes, as an interpreter. But I would say it is built on top of Clang and LLVM, and it has compiler and interpreter parts. And I'm saying that because we changed a little bit the granularity of things. Instead, a normal interpreter will do line-by-line processing, and then you'll get the side effect immediately. We changed the granularity to processing function per function, or top-level declaration per top-level declaration, and then we figure out which things have to be delayed until runtime, and those things are escaped and then recompiled at runtime. And depending on building it on top of Clang and LLVM doesn't bring any cross dependency. You don't need to have Clang installed, or you don't need to compile neither Cling or the project using it with a particular system. So what are the key strengths? As I said, the key strengths are full C++ support. That's one of the most important things. And this approach gives us a way how to go to the upcoming C++ standards, because we're going to inherit it virtually for free from the compiler library. And we get very stable and informative intermediate representations. For me, it is absolutely fantastic that we have the AST of the source code, which is properly built without losing any information, and we have the LLVM intermediate representation, which is, again, as you might have seen from the keynote talk, it is very informative and descriptive. So, and it's being developed in mind that it's going to be used in multi-threaded environment. So we will have it's designed to be used as one interpreter per object, and its type engine is separated from its execution engine, because you still want to query the type database in parallel, and this just didn't work. And here you can see how it feels like. That is very, very straightforward. It doesn't make any sense, but it shows that we don't have any issues with templates. I can have vectors of maps of I don't know what it is. Sets and strings and whatnot, and it just works because we are using the underlying thing. Of course, we have bent all the interfaces to make it work that we want, but in the end we haven't patched the parser or we haven't reinvented the wheel. And it does pretty well with C++ 11. You're going to have lambdas and stuff. And here, more importantly, is that the upcoming standard is going to be directly inherited from Clang. And of course, here, yes, you can have lambdas in templates and whatnot. And I just put it because I imagined what would have taken us if we had to implement that in our previous stuff. It's totally amazing. And now we can even dare to think about Boost. In the past we couldn't think of using full STL, and now we can even dare to think about it. And it mostly works. Here I'm able to use the random generators and stuff like that. But right now, this is a limitation coming from LLVM that the current JIT doesn't support inline assembly, which I'm being told that the MC JIT is going to fix. And this is something that we need to do. We need to do the transition. And having that in mind, that this is going to we are going to be able to use Boost. And of course, yes, that is going to, I'm going to talk things that you already know, but I'm going to skip through it. I know that the diagnostics are important, and I guess you know that as well. But I want to emphasize that in our case, when we have novices and when you have people that are trying to find their way through, the diagnostics are extremely important. And I am absolutely fascinated with what we get for free with Clang. We get things that are, for me, that are really, really, really nice. So I'm going to skip through it, and probably you already know about that because it's default in Mac. That was something which was a trend a year ago, or at the time that you didn't get Clang on Mac. But in that case, when you have range highlighting and carrier diagnostics, that's really, really helps when you develop interactive applications. But not even interactively, but it's even more helpful. So in the past, we had very weird extensions. In the past, we had very weird extensions where, for example, if you use arrow instead of dot, then the interpreter, our old interpreter, would flip that back and transparently to the user and fix it for you. And then you would get that code and port it to the compiler, and then you would say that doesn't work. Because, yeah, it doesn't work because it's not C++. But here, in that example, with the diagnostics that we get, we don't even think of trying to port that extension, right? Because it's absolutely straightforward. You know what you have done and what's wrong. And the fixed hints, again, it's fantastic. Probably the drawback is that the fixed system is not that open. So probably we would patch something in which makes it a bit more adapted to our usage patterns. But I'm pretty happy with what we have right now. You have the fixes. If you screw up a name, which is most of the cases, you don't even need to look at the source code. And even with the complex examples where we have, in that case, if you have that in mind, it's pretty obvious that you have a virtual method that is coming through two base classes. And that is really hard to diagnose with a compiler. And what you have here with Clang, it's, if you do that kind of mistake, you don't even need to look at your source code. You immediately understand what happened. It says you're trying to override a function which is ambiguous, and I don't know what to do. So go fix it. Templates, that's a huge improvement. You have the template instantiation chains. You understand immediately without printouts what happened. No things like, yes, that's in an ideal world, but it's a lot better than anything else. And macro expansions as well, I don't want to stop on that because I am running out of time. Before that happens, I would like to talk about a little bit more about the architecture of how we do that. What do we do and how do we do it? So what Clink is essentially it's a tiny tool that is built on top of Clang and LLVM, and it tries to orchestrate them. And what the user would do is the user would query Clink, and Clink would aggregate the compilation engine from Clang and the LLVM execution engine. And then what would happen is the user start poking the interpreter with text, right? This is the way code works. You use stuff in text. And then Clink would ask Clang for to compile that piece of code. And then Clang would return in the cases where there are no errors, would return an AST. And in the cases where that is not compilable for Clang, but Clink expects that to compile, we orchestrate the compilation process. We mark certain things as dependent. We do healing, AST node healing, and stuff like that. And once we're happy with the result, and that's done by our transformation engine. We have that transformation engine which you would give it an AST, part of the AST, or it would hook in some callbacks in Clang and then try to fix things, to make it work the way we want. And then once we're happy with it, we would ask Clang to create the LVM IR and then pipe it through the execution engine and run it. So the way it works via well-defined channels in Clang. So that thing works in sharing those intermediary representations which are well fixed. So that is the communication channel between you share an AST, you start doing things with it, you fix it in the way that you need, and then you go on. So again, that's communication between the transformation engine, and in the end, you ask the execution engine to run that bytecode for you, that bitcode for you. And what is the execution engine? The execution engine is the current LLVM JIT, and you would ask it to produce target-dependent code, which is specific for that target, and it would produce it natively. And then you would easily call that. You could easily call into libraries, and here I can call into native libraries using the fact that the JIT has the full knowledge about the target information, about the target and the ABI rules, how to call functions. Of course, there are other options. We can use the LLI, the interpreter, but it's not very highly recommended. And what we're looking for is the new MCJIT, which is set that it's going to be able to process inline assembly, but it's missing very, very important part. It's missing the lazy function creator, which we heavily rely on, but I won't cover that. I don't have enough time. So what usually happens, how Clink, the way Clink works on the prompt is it will create a transaction. A transaction is something which is a bunch of declarations. So on every input, you compile things with certain compilation options. For example, and this would produce a transaction. And then on the next input line, you can, in the meanwhile, change the state of the way you compile. And then on the second bunch of transactions, you would get different compilation options and so on and so forth. And what we do is we have nested transactions for the things which are caused by a code that's being recursively parsed by somebody who is in the middle of execution and parsing. So this happens when you do the string-based lookup, because this is parsing that part of the code, and then it goes into Clang, and then then it causes another parse, but those are dependent things. So those declarations, and in that case, this is going to cause a declaration, right? Because in the cases where we ask for the std vector of int and it's not instantiated, we want to instantiate it. This is our use case. That's how our reflection layer works. If it asks for an instantiation, you have to produce it. So it's not lookup in the sense of how it's defined in the standard. So that's what why I say find. And there are things that you can reuse in Clink. So the transformation engine can be queried by transactions, and the transformation engine contains the so-called transaction transformers, which run on that transaction, transforming it in a way that it makes sense. And this is how we have implemented almost all our language extensions, which I'm going to show you briefly. And we have interpreter callbacks where you can further specialize everything. And you can, as a matter of fact, this is the way how we implement our reflection layer, how we communicate. Because if something happens here, if a new declaration is seen, then the client needs to be notified. And in our case, we notify for query bunches of declarations. So there were a lot of challenges, and there are still a lot of challenges. But the biggest challenges nowadays is that we want to make it as usable as it was our old interpreter, and it was very useful on the prompt. So what we want to be able to do is essentially we want to type statements. You want to run statements, and you want to do, for example, sinus of 12, and you have to be able to run it and get the results back. And the way that we do it, of course, is not you cannot have statements on the global scope. This is not supported by the standard. So what we do is we wrap it in a function and we run that function. But there is another level of complication. What do we do in the cases where you declare things, right? Then you have those usability issues, because I has to be seen by might be reused by the upcoming wrappers. So the way that we do it is we scan for declaration statements and we extract it one level up. This means we extract it on the global scope, and extracting that, this means that we have to deal with static initialization, right? Because static initialization, in our case, means that we have to incrementally run the static initializers, which is something which is not very straightforward, so to say, for the way how it's perceived in C++, right? Here, I want to run that. I want to initialize I before I do printf. So that's okay, but next time if I do J here, I don't want to reinitialize I, right? So I have to do that per incrementally. And again, on the destruction part, I want to keep the destruction the way it was. And that easily becomes extra complicated when you have int I equals something, I plus plus, and int j equals I. Then you have to initialize I, then increment it by 1, and then initialize j, because otherwise you get different semantics. And what we want to be able to is easily to get the results of execution. The execution results have to be easily, without printfs. You don't imagine that you had to do printfs every time that you run something. That's totally insane. So in that case, we implemented an extension which you just omit the semicolon from the last expression, and if it can produce result, you get it. And of course, here we have precise type information. I think I said that way too many times. So, and then we have another sort of extension which is GDB-like, when you have instead of, if you omit the parentheses of the function, then it prints the source code if it finds it. So something which is very, very essential, and maybe I should have put it first. So for the interactiveness, we cannot afford to quit, right? We cannot afford on error to crash, because suppose that the user have typed like hundreds of lines of code and he almost got it. So on errors, you have to survive, but it's not that simple. In that case here, what would happen is that you have the first declaration eaten up by the compiler, and then you have an error, and then what do? You have to discard the whole input. So you have to go back, you have to fix all the internal structures of the compiler, so that you make sure that it forgot I, so that next time the user tries to rerun that thing fixed, it should be seen as it was seen for the first time. And that thing blows up when you have template instantiations and stuff, because it's very, very hard, because the template instantiator does a lot of complex things on the backstage. So you have to fix the lookups, you have to fix the internal structures that are holding the specializations and the instantiations and things like that. And suppose that you do bound include vector and an error afterwards. So that thing has to revert the whole of STL, which is extremely, extremely tricky. What we have is we have different other GDB-like extension where if you do that and I is not assigned, is not defined, and you have the initialization here, you deduce the type. So this is a sort of what I call implicit auto keyword. So we have to support omission of auto in front, and then make that thing work. So you get the initializer. It's not an initializer in that case. It's a binary operator. But you have to get the right-hand side type and then fix that one. So that is a little bit tricky. So the way we do it is we mark that thing. We see that there is a failed lookup, and that lookup, instead of issuing an error, we define a dummy declaration of dependent type, which would silence that, and it is going to be transformed into yes. Yes. I want to implement that optional. Yes, absolutely. So the question is that optional? Yes, it has. Right now it's not, but my idea is to make it optional. It has to be optional. So the way we do it is we mark that as dependent. It becomes a binary operator, and then we go and fix that, because that declaration which was marked as dependent, we annotate it so that we filter out the rest of the things that were marked as dependent from the compiler and stuff like that. So other very tricky to implement extension it still is, because I've implemented that, but our test suite doesn't pass. So as long as the test suite doesn't pass, it's not implemented for me. So what you have, suppose that let's consider again root files. We have that thing. We have some condition. You open a file which contains something, and that thing is dependent on the runtime, dependent on the day of what it is today, or things like that. So you load that, and remember that in those root files you have C++ objects, and what you want to have is you want to use that. You want to use the names of that contained in those root files as if they were defined somewhere. So far, okay? In a sense, you want to, when you open a root file, you want to extend the lookup such that you can be able to run methods from objects defined in root files. And this doesn't compile, of course. So what we do is we use basically the same approach. We escape the things. We see that there is a root file here open, and we see that there is an unknown symbol, but we say, okay, we can't say whether that's right or wrong at compilation time. So what we do is we escape it. We wrap it in a function call, which okay, yes, it opens the dynamic scope and so-called we call it dynamic scopes, and what the compiler would do, because you have to be able to compile that in order to continue on. So what you would do is you would convert that as a function which ensures that this is runtime. And what we have some sort of an instance of the interpreter inside the interpreter itself. It's some sort of, you can think of it as compiler or service. And then you would query the interpreter at runtime to reparse that. And by that time, our root file has to be loaded, and then you can go to the callback and then get the information that you needed. Otherwise, you just issue an error. And that thing, yes, and that thing usually becomes very, very tricky, because you want to bridge basically both worlds, right? Here, if you have variables and you use that symbol in some context which expects a return type, you have to export context from compile time to runtime so that you get it work. And the way we do it is, because at compile time we don't have the addresses of the current arguments here, what we would do is we would create a mask escaping the type, would put a placeholder for that argument to be put at runtime, and then we would instantiate that trampoline function with the expected return result, because usually at the context where you use it, you know what you want it to return. And in the case here in the if statement, you know that it has to be bool. That's by definition. And yes, that is one of the tricky parts. So if that you consider as tricky, we can go one step further. I'll show you how we have to be able to unload code. And this is a very common use case. You have your header file, you have your code, and you implement it, and then you run it, and then you see that this doesn't behave that you want. This is a semantical issue with your code. It's not a syntax. So you go fix it, then you want to reload it, which means that you have to forget all about that. So you have to forget everything to certain restore point, and that restore point here is considered as a bunch of transactions. So you have to revert everything from the AST and the compiler intermediate representation and the execution engine and the memory, which, because this was already JITed here. So that is very, very, very tricky, and that's nothing even close to what a compiler was designed for. And we're able to, right now I'm able to unload simple things, and I believe that this is going to happen by the end of, the unloading is going to happen by the end of the year. So, and of course, since we rely on the underlying compiler, we can do a lot more than C++, because Clang can do a lot more than C++. Of course, CERN is not interested in developing, in making Objective-C to work. But without any efforts, I'm able to run a simple hello world message without retains and these kind of things. I think it's called ARC or something. That support has to be patched by loading the proper runtime. And I wouldn't say it's very difficult to get it right, but still. So what else? We don't like parsing, and especially we don't like parsing of things again and again, which are invariant. So we were able to hook in PCH support, but in the root use case, PCH support is not enough. PCH is precompiled headers, which are pre-parsed and pre-analyzed things that you just hook in, and you avoid the time that you usually would spend in parsing the same thing. But the main issue there is that since root is used as a part of the experiment software stack, building one PCH would mean that if you have a single change in your experiment software, this means that you have to rebuild the whole thing. And you imagine rebuilding the PCH for 5 million lines of code. It doesn't just work. So what we are really interested in are the so-called PCMs, or the C++ modules. I don't know whether you are aware of it, but there was a very nice presentation about it. And this basically is going to be able to merge the differences from the certain library instead of rebuilding the whole thing. If you have changed a certain header file from a certain library, you should be able to rebuild only that one, and then what happens is you're going to pull it in, and then the compiler is going to merge the definitions. And of course, we want less jitting. And right now, the current JIT uses, well, there is no other way around, but in our case, it slows down a lot of things in our reflection layer. So for the argument setup, the LLVM JIT uses trampolines so that to do the conversions and stuff like that. And most of the times we don't need to do it. So we have to be smarter, or we have to pass something to the JIT or something like that. So smart optimizations of the user code, as I said, user code is a jungle. So what we would like to have is to be able at least to do the devirtualization stuff where, I don't know, a user calls millions of times the virtual function in loop or something. So, and here, I believe that all the ingredients in LLVM for creating a tracing JIT are there. So I just would like to understand what are the missing parts of creating a tracing JIT, so that we can be smarter and we can instrument the code and be smarter in balancing the interpreting and the JIT compilation. And based on samples, we could eliminate certain things from execution. So what are the future plans? And by future plans, I mean I have limited time at CERN, so those should be I wanted to make it very recent plans. So I would like to migrate to MCJIT as soon as possible, because it gives us a lot of things, a lot of advantages, and boost, of course. And many of our users are delighted from the fact that they could use boost in their code. I don't know, they just want it. Yeah, I don't know what is their reasoning. Of course, it's a fantastic library, but if there is something out there, they want to use it, and we have to be able to provide that, to be able to give it to them. The next thing, I would like to understand what are the missing features for supporting Windows 64 ABI, and I've seen on the mailing list and some work in that case, but in that respect, but I have no idea what is missing. I think the virtual bases and stuff are missing, but anyway. So null pointer dereferences are things that, for example, if you are in the Clink prompt, you have to be able, Clink has to be able to detect whether you are calling something on a null pointer, because otherwise it's going to crash. It's going to do segmentation violation. Of course, you can do long jumps and stuff, but that just doesn't. It's not the way to go. So this is going to appear very soon. We have a Google Summer of Code guy working. We should have a Google Summer of Code guy working on that. And as I said, we can start working on tools. And automatic differentiation is a fantastic tool that we would like to work on. And I spoke with Joel about that. On the Booth library, there was a thread, I don't know, 2010 about that, and that thing, I have no idea where it goes. So here the idea is to create that automatic differentiation tool is to, instead of do operator overloading or things like that, you'd ask the intermediate representation for the function that you want to differentiate, and then you would build from the AST directly the nth derivative of that function. Yes, so that is pretty much it. And here are some references. There are some interesting use cases outside our use case for clean. You can go visit them. And that is the website. I forgot to put root website, which I should fix. It is root.cern.ch. But if you Google root and CERN, this is going to appear. Yes.
Back on the frontline interpreter. How well does Practicopathy start launching threads, for instance, when they are using the futures API?
So the question is, what happens if you use the interpreter in threads? Is that correct? We haven't used that yet. I can't say. We haven't used that. It's on our to-do list, but our manpower is limited, so we didn't try. I can't say. And there are a lot of other references because I did a lot of things trying to explain what CERN is, and if somebody is interested in that, you can go check it out. And yes. So and in the end, that is all about, right? All that huge thing is that is all about. That's a simulation of one of the channels that they expected the Higgs boson. So all the data is trying to fit, and they're trying to find signals that are indicating something interesting, which their model is predicting or it's not. So that's pretty much it. Thank you very much.